today is going to be seawater reverse osmosis. And the reason for that is that is now the dominant technology that is being installed worldwide for seawater desalting. Seawater reverse osmosis process is really quite simple. You take the seawater, you pump it, you filter it, and you chemically modify it to make it suitable for the reverse osmosis process. You then pressurise it against the reverse osmosis membrane in order to overcome the natural tendency of osmosis that when you place seawater against the membrane, for water to diffuse across that membrane and to dilute the seawater. As you take the seawater and you remove water from it, pure water, the seawater will concentrate and increase in concentration. In a modern seawater RO plant, it will have a recovery of about 50%. And what this means is that as you pass the seawater through the reverse osmosis plant, the concentration will increase from 35 grams per litre up to about 70 grams per litre. To achieve that, you need to pressurise the seawater to about 70 bar, again to overcome that natural tendency for osmosis to occur. After you concentrate the seawater, it becomes a brine that needs to be disposed of. The pressure energy in that brine is usually recovered and helps pressurise the feedwater, and then is disposed of generally to the ocean. The water that is recovered goes on to post-strip where it's chemically modified to make it suitable for drinking and reticulation. After that, it then needs to be pumped to the storage and distribution system. The key element of this overhead is energy. That is what is required to make this process possible. And it's required mainly for pressurising the seawater for reverse osmosis to occur. But it's also required in other components of the process: pumping the seawater, pre-treatment, energy recovery, post-treatment, and storage and distribution. Now this is important because energy is the dominant factor in operating costs for seawater desalting. And this is an example of a cap operating cost breakdown for a seawater desalting plant. And as you can see, electric power is about 60%. So if we want to develop a cheaper seawater desalting technology, we have to do something about the amount of energy that's required. And for most of it comes from the reverse osmosis process, we have to find some way of decreasing the energy consumption. And to answer this question, we need to know about thermodynamics. Now, I can't give you a lecture on thermodynamics today, but on the next overhead, I have the results of my analysis. So, to put this in context, we take a look at the desalting plant proposed for Adelaide, and we take a look at the size, the energy, and electricity, and the carbon requirements. For a 50 gigalitre per year plant, the energy that's required, assuming it's 3.5 kilowatt hours per cubic metre, means you need a power plant of about 25 megawatts. That's about 1 to 2% of the state's average demand. The amount of carbon it produces is between 90 to 150 kilotons of carbon dioxide per year. That's only about 0.01 to 0.03% of the total greenhouse gas emissions that occur in Australia annually. To take a look at cost, now you've probably heard a value of 1.4 billion mentioned for the cost of the seawater desalting plant of about 50 gigalitres per annum for Adelaide. In Perth, they built one, 45 gigalitres per year, 376 million. In this table, I compare the cost of building Adelaide's desalting plants for those two scenarios and how much it will cost for a unit volume of water. First scenario is 500 million, the second scenario is 1.4 billion. At the bottom, if it's 500 million, it's going to cost $2.85 per cubic metre. If it's 1.4 billion, it will be $4.83 per kilolitre. The effect this will have on water pricing, if we take a look at current pricing, it may come as a surprise to you. We currently pay between about $1.35 to $1.53 per kilolitre of water when you take into account the fixed quarterly charges. This is the current pricing. If the price is raised to $2.50 per cubic metre, which is what I estimate will need to be done if we have a seawater desalting plant providing about a quarter of Adelaide's water supply and the new infrastructure that's proposed, it will increase the bills per quarter for someone using 200 kilolitres by $48 and 400 kilolitres $115. The typical consumption in Adelaide is around 284. So my concluding remarks are, if we want to make some advances in seawater RO technology, the first thing we need to do is try and approach the minimum theoretical energy requirement. We're still about 2 to 2.5 times above that with modern seawater desalting plants. And if we take a look at the information I've put on that overhead, if it costs $1.4 billion to build a plant, and that contributes about $2 per cubic metre, we need to find a way to decrease the plant capital cost. And that involves development of new and more cost-effective membrane technologies and processing paradigms. Thank you very much.